distinguished professors and my outstanding students. I'm Meng-Chi Chen, and you can call me Ed Chen. I'm a senior student in Department of Chemistry, National Tsinghua University. And my advisor is Professor Jer-Shing Huang. And I'm really excited today to present you with my work. My work is about using eddy current to sort gold microplates according to their size. And as you can see in these three GIF files, and the gold microplates will move to certain direction, and because of the time variant magnetic field. And I'm in oral 6 at page 73. So what's eddy current? Eddy current is basically a electric current that is induced by time variant magnetic field according to Maxwell's equation. And let me show you something. This is a magnet, a very strong magnet, and these are two pieces of aluminum. It's not magnetic, it won't attract. However, if I put this here and put this strong magnet very close to the aluminum and I push it, the aluminum piece will be jacked by the magnetic field. And also, if I put the magnet in between these two pieces of aluminum, the magnet will drop very slowly. And these all because of eddy current. A magnet have north pole and south pole. That will generate a magnetic field like this. For the cleanness, I will represent it as this way. There is a non-magnetic conductive plate such as aluminum, gold, or silver. If it moves in this direction, for the material that is approaching the magnet, it will generate an eddy current that also generates an induced magnetic field that fights with the external magnetic field. So there will be a repulsion force. And for the material that is leaving the magnet, it will also generate an eddy current. However, it will attract the external magnetic field. So this repel and attract force will end up a retarding force and heating effect. And what are the applications of eddy currents? And there are eddy currents brakes that are used on high-speed railways, and induction cookers that are in our kitchen, and eddy current separator that are used to separate aluminum can from non-magnetic waste. And microfluidics heater that they use a conductive plate put in a microfluidics and apply time variant magnetic field to induce it. It's kind of like a micro-scale size induction cooker. And non-destructive testing and magnetic hyperthermia. They use conductive nanoparticles that inject into the body and they use external time variant magnetic field to heat up the particle, and the heat will shrink the cancer cell. In our group, we use a lot of chemically synthesis gold microplates, and we study the light matter interaction such as surface plasma with these gold microplates. However, they usually result in board size distribution, like this and this. So I want to sort the gold microplates with eddy current according to their size. And this is our principle, another definition here. I have two magnets that align in this way and they will move in this direction. In between of them, they will generate a magnetic field like this. There's a container which is fixed, and the magnet moves in this direction. Suppose there are two gold microplates here. The one will attract by the magnet, and the other one will be repelled by the magnet. And the net force is that the gold microplates will move along with the direction of the magnets. And our sampling procedure is that there's a glass container, and we made a PDMS container with it, and dig a hole inside and put our gold microplate solution in water into it and seal it with another piece of gas. And this is about 8 mm thick, so that it can be put into our rotor. And our rotor is a piece of aluminum that there are 8 magnets on one side and another 8 magnets on the other side, and there are 2 discs of them, so that they rotate at a very high speed, about 1,450 RPM. We can put our sample in the in-between side where there will be a stronger magnetic field, or put it on top side where we can use microscope to observe the sorting phenomena, because in this in-between side there is only 1 centimeter gap, and we can put a microscope inside. However, this kind of container have a little problem, is that before every experiment, we need to put our sample into the use ultrasonic to shake the gold microplates so that they won't aggregate together. And every time I use ultrasonic, the bubble will generate. So I made another container, and it's an acrid tube. I heat it up and crush it down and allow it to anneal very slowly. And I can have a structure like this. I seal it at one side and seal it at another side, so bubble will gather here, and I can make a clean observation. And this is our sampling method. Suppose that magnet moves in this direction, and we separate we divide the length of our cell into 20 sections, and we took pictures in each sections, and we did it for 3 trails and do an average, so that if the magnet moves in this direction, we can expect there are more and larger gold microplates here and less and smaller gold microplates here. And this is our setup for the in-between site. And this is our sampling method. We use a microscope to see, to take pictures in each section and calculate the size and number of gold microplates. And this is our setup: a motor, drive a rotor with a belt, and there's a microscope on top of this so that we can observe the result. Next, we want to do some calculation about how, if the eddy current force can really push the gold microplates, because the gold microplates is so small, and it's also so light, and it's also very light, so that we can push it easily. But how can we actually push it? So we make a calculation. We made a measurement of our rotor. This is our rotor, and we put a Gauss meter, which is a device to measure the magnetic field strength here at the in-between site. So we did so in every revolution, it will generate a magnetic field like this, because there are 8 magnets, so 1, 2, 3, 4, 5, 6, 7, 8 magnets, and we do the Fourier transform for our magnetic field strength, and we have regenerate with it with a sine wave like this, and you can barely see the blue line behind the red line, behind the yellow line, because we fit it really good. If you don't have a concept about how big 0.7 Tesla is, I give you an idea that 1 Tesla equals to 10,000 Gauss, and single one of magnet I just show you can generate 0.5 Tesla, and typical refrigerated magnet is about this big, and Earth magnetic field is about this big. So here is a calculation. According to Maxwell equation, if we want to approach our calculation this way, it will be really complicated. So we approach in another way. We suppose the gold microplate is a square, and there are 2 forces that we want to analyze: an eddy current force and a drag force. And we want to know its speed. So we start with Newton's second law, and thankfully we find an research that is studying the force exists on the magnetic braking. So we will have a differential equation like this. Following, we will apply our calculation to our gold microplates. One is 20 and the other is 4 micrometer long. And the result is that the force on these 2 microplates have significant difference that we believe we can separate them according to their size. And And we want to analyze the movement of our gold microplates. This is the magnetic field strength, and if we see here the first red line, when there is a dramatic increase at the magnetic field strength, which means dB over dt is very huge, and we'll have a lot of acceleration like here. And if there is no magnetic field change, there will be no acceleration. And if the speed is very fast, the faster the speed, the greater the drag force created by the solution, which is water in our experiment. So the speed won't go high, keep going high, and it will drop if the speed is too fast. Next, I want to show you my in-between site result, which we put our sample here, and this is a blank test that we calculate the number of gold microplates in each section, and the magnet moves in this direction. So we can expect the following picture will have more gold microplates here. So yes, it is. It has more gold microplates here, and this group of gold microplates is the smaller gold microplates that cannot be moved by the eddy current because it's too small. And if we draw a 200 line here, you can see that in the front area there is an increase of the number of gold microplates, and in the rear area there is a decrease of gold microplates. So we can prove that our eddy current effect can really move the gold microplates. And how about size distribution? And this is about the size distribution. We define the big microplates are the size over one, are the size 1 over 1 times 1 micrometer, and there are more gold microplates here and less gold microplates for the smaller microplates here. And for the smaller microplates, there are more gold microplates in the rear area, so we can separate the gold microplates according to their size. For the on top side, we have a different result that, wait a minute, that if our magnet is moves in this direction, the gold microplate is moves to the opposite direction, which is strange. And we think that is because if it's in the in-between site, the magnetic field is uniform and is strong. And however, at the on top side, the magnetic field is weak and uniform. So at the on top side, this is a magnet, and it will move in this direction, and so it will create a magnetic an eddy current force larger here, and eddy current force that is smaller here. So that will generate a torque that make the gold microplates roll backwards. So it will move on the opposite side where the magnet moves. And in the previous picture, that we can see only some of the gold microplates will move. Not every gold microplates will move very fast according to with the direction the magnet moves. That we think this is because the van der Waals force between the gold microplates and the container is too big. So there is an ongoing work that we attach a vibrator on our sampling tube, and the function of a vibrator is to create a force that dissociates the gold microplates with the wall of the container, and we hope this can enhance our performance and reduce the sorting time. And this is the latest result that before the experiment, we changed another way to do this experiment. Before the experiment, we align all the gold microplates at the single side of the container. And we did a blank test, which we only vibrate for 1 hour, and there's no magnet moving. And the real experiment that we sort 1 hour with vibrator, we can see that there are larger gold microplates on the top side here, and smaller gold microplates here. So there is sorting effect here. However, we hadn't do a quantitative test for this result. Okay, I would like to conclude my work here that we successfully demonstrate that we can use eddy current to affect the size distribution of the gold microplates, and we observed that eddy current can really move time variant magnetic field can really move the gold microplates, and we'll have a nice result here. And my talk is finished here, and questions and comments are welcome.
So we can have some questions. Any questions? Comments?
Yes,
nice talk, but I still don't understand how you can use this design to separate the different size of the gold plate, because I think this is your purpose, right?
Yes, and according to our calculation, we found that the gold microplates with larger volume will have larger force that affected by the time variant magnetic field, because the demonstrator I just showed you. And the difference between big plates and smaller plates are the cross section. They have different cross section to the solution, right? And the different cross section will have different jack force. So the smaller gold plates will have smaller jack force, so that it will if both of them have the same speed, same force according to their volume, and the smaller one will move slower, and big one, the big one will move faster. Did I answer your question?
Well, it really depends on the top view or side view. So I don't know what do you mean about the cross section, because for the force, I think it's a normal projection, the cross section. But for the jacking force, it's a side cross section. So there's a two balanced force.
Yes.
The two forces, they will balance each other. So I don't know because there is one is induced force, and another one is from the water. So I don't know.
Well, you can think in the other easy way that the bigger size will have a larger area to let eddy current to be induced, and larger eddy current will have larger induced magnetic field that fights with the original magnetic field. And this will larger than this force increasement according to its area will increase faster than its weight, so we can easily move them.
Thank you. Thank you.
Any other question? I have one question.
Yes.
Because the large and the small pieces are mixed, right? So when they are moving, and there will be collision, right?
Collision?
Yeah.
Sure.
So it kind of another force to prevent the moving of the larger pieces.
So,
right?
You mean collision, the force that will...
Because of the different sizes of particles moving, so there will be a collision.
Yes, sure. That's a good question. And we are trying to reduce the concentration of our gold microplates to reduce this effect. However, if we are going to calculate the collision force, the whole system will be very complicated.
But particle, there will be a kind of the mixture will be of high density, right? And you try to sort in different pieces. So I don't know, maybe the collision might be an important factor for sorting.
Collision is random. However, the eddy current force is to a certain direction, so it will eventually move.
Yeah, it will move, but due to the collision, so it's not necessary that the bigger pieces will move further, right? Depends on the collision. Yeah.
Yes.
Okay.
Yes, thank you.
I think the eddy current depends also on the skin depth. So do you think you would be able to source different conducting materials of the same size but different materials?
You mean the...
Say gold, aluminium, and copper.
Oh,
you will have different eddy currents probably, but
Oh, according to our calculation, wait a minute. Okay. Okay, as shown here, the force. There is a parameter here is a function of conductivity.
Yeah.
And we haven't tried a different material in the same solution, but the different material will have different conductivity. So I believe that we will have a result, but it won't be obvious because maybe their conductivity is really close, and we need to do the calculation to make sure of it. That's a good question. Thank you, Professor.
So let's set the speaker again.